Okay, you'll want to start up XFLR 5. You'll get this black screen. Go to Direct Foil Design. Control 1 alternatively. You're going to want to define some airfoils. For this basic analysis that we're doing, you don't have to go out on the internet, find airfoils, download them, do all that stuff. Because the basic characteristics we're looking at for this first pass of general performance, just for trade studies, it isn't interested in that level of detail. So you can just use NAC airfoils, which you generate on the spot. I'd recommend just use the 4 series, and the way that goes is the first digit is the percent camber, and that's percent as a relative to the chord. So if you had 100% camber, that would mean the camber line deflects upward by just as much as the entire airfoil is in chord. That would be ridiculous looking. So just like 2% camber is a pretty normal airfoil. So we'd start with a 2, and that's how much it's deflected up, measured at what point. You'd say at like 40% of the chord, somewhere in the middle. You don't want to specify the camber all the way at the front, because it's always going to be 0 up there. And then the percent thickness. So again, this is relative to the chord. So a 10% thick airfoil is exactly 1/10 as thick as it is chord long. So let's do 10, 2410. And it automatically generated the name 2410. So let me make this a little smaller so my head's not blocking it. You can see the options and my wonderful background. You can look at the points that actually generate the airfoil and the center line, which is your camber line. It's calling it the center line because it's literally the center. If you look at each one of these point pairs, the center line is exactly between them, which is the definition of the camber line. So it's using a little bit definition here, but it's talking about the same thing. So you can see it even tells you this NACA 2410 has 2% camber at 40% of the chord. So just as another example, if you want a symmetrical airfoil, which you should use a symmetric airfoil for any stabilizers in your analysis, horizontal and vertical stabilizer. I'm talking about the tail surfaces in the back. Or if you have like a delta wing or something, you might not necessarily want camber. I'm actually going to be doing a delta wing, so I'm not interested in that. So you maybe have a 0010, no camber. Second digit doesn't matter because you already said no camber, but 10% thick. So that's the same thickness airfoil, but no camber. Yeah, 0010, you see that? And if I just show the 0010, you can see the center line is right along the, these are airfoil coordinates X and Y. So it's right along the airfoil coordinate x-axis. If we want to make a really, really thin airfoil, like to kind of just be a flat plate, you might do something like a 0004. Yeah, and there's a really thin airfoil, 4% thick. Okay, so we've covered generating airfoils. You want to generate a good sample of whatever you expect your aircraft to have. Now, I kind of glossed over this, but presumably you already have an idea of what your aircraft configuration is like and what you're looking at. Hopefully you have a sketch, because the next step is plane design. So go to wing and plane design. And it might pop you into polar view, but you can hit 3D view up here. And this plane analysis thing might be undocked, in which case you can just kind of drag it over there to dock it. Or I think you can double click it. Let's see. Yep, double click. Great. So hopefully you have a drawing. I drew out, this is kind of modeled after the Viggen, which is a European fighter. It's just a Delta aircraft with a canard. What I did for this sketch is I just started with some actual distance, like I wanted the wingspan to be 1.2 meters. So I drew out what the I drew out 1.2 meters and then drew the whole plane off of that bottom trailing edge line. It just happened to work well for this design. You can pick anything, just make sure that you've identified a scale. So doing that as 1.2 meters ended up being that my scale, if you can see it, is 50 millimeters to a side on this graph paper. This is engineering paper, so it's kind of faint, but it is graph paper. So that means that I can easily, now that I have this sketch, figure out where each point on the aircraft is in 3D space and easily populate the vehicle geometry. Okay, I forgot to put this clip in there, so real quick, adding it in during the editing process. After we do direct foil design, you need to go to wing and plane design. So that's File, Wing and Plane Design. That's Control 6 if you want to use the shortcut. And that's how you get to this point where I'm going to talk about in the next clip. These different menus for polar and aircraft. If you're not seeing these up here, you might still be in direct foil design where you'll see different buttons at the top. Okay, that's it. Don't forget to save. So you'll want to save. I'd recommend go to the Aero folder in our repository, Aero XFLR. Create a new folder. I'm doing the vegan, so I've already made the folder and I've named it. And put it in your XFL project file in here. Okay, now that you've saved it, you're going to define a new plane. Up here, you go to plane, define new plane. I've already defined my plane. So this is the default that just popped up. I have to edit it. So I am going to current plane, edit. This is the vegan medium. Of course, it doesn't look like that yet, but that's what we're about to do, right? How do you set the geometry? Okay, so all of the wing, elevator, fin, wing 2 operate the same way. You're just specifying different sections, like a root chord and then a tip chord, and you're specifying what's the distance between them, is there any offset, and what's the size of each one. So I'll show you. In the main wing, let me get some foils on here so that you see it three-dimensionally. So there we got a great 3D wing. You can see that it's highlighted in red, the root airfoil, and that's because I've selected this first row. So this first row is all about specifying where that airfoil is, how large it is, what is its relative orientation. To select the second row, you see it's highlighted the tip, and that's defining where the tip airfoil cross-section is, all that. And then it just lofts between the two. So this is a simple two-section, and you can see that's the terminology it uses. You can insert another section before section 2, or after section 1, same thing. Now, let's actually go through what each column does. Okay, so Y in millimeters, you can see here on the coordinate frame, y-axis is this way. So this is saying how far from center is this section defined. So the root section obviously is going to be at 0. If you put some offset on there, which you can, you'll see now we have an awkward gap, which, I don't know, maybe depending on your aircraft you might want that, but I'm going to put that back to 0. But the more important thing is coming into section 2. When you specify Y for this section, you're basically specifying your wingspan. So by setting it to 500, that's 500 millimeters from the root chord out to either one of these panels. So the one which I'm circling in the bottom left here is positive 500 Y, which means the overall wingspan, positive 500 and negative 500, is 1 meter. Now I'm looking for 1.2 for my vehicle, so I'm going to put in 600. Now the second column is chord, which is the length of each one of these sections. So, oh man, looking at my drawing, looks like the root chord I want is freaking massive. I'll just throw in something real quick to show you how it works, and then I'll go through and actually make everything match my drawing in detail. So we'll say 1400, and the tip chord is about 250. So I'm trying to create a delta wing, but you can see that if it's flying this way, it's actually kind of backwards. So this is where the offset comes in. The offset is saying where is the leading edge of the section in the X direction. So the first section here has 0 for the offset, which means that its leading edge of its section butts right up against the origin for this coordinate system. The leading edge for the outer section, section 2, is 70 millimeters back in the X direction. So if I increase that, you can see it is offset even more from the y-axis along the X direction. So I actually want the trailing edge to be flat, meaning that the offset plus chord of the second section should match the chord of the first section, which means I'm looking for 1150. Now that looks like a proper delta wing, but I'm going to go with that thin airfoil I generated and add some more panels. So yeah, I kind of glossed over real quick, but this column over here is where you select the airfoils you generated in the first part in airfoil selection. If you don't like the airfoils you generated, then let me save this. Okay. The tails still need to be fixed. That's funny. You can always go back to it. Direct foil design. You can change them. Go to wing and plane design, and then there'll be an option for you. So again, to edit the plane, current plane edit. Now, what about these columns I skipped? These are less important usually, but they can certainly be important to your design. So there's dihedral. You'll notice there's no option for the second section. It's only an option for the first. That's because this column specifies the angle that the wings deflect upward. And so it's specifying that angle from this section to the next section. You'll just see real quick if I type it in. So I've deflected it 5 degrees up. Specifying it for the second section doesn't mean anything because there's no third section. So let me show you a third section example. Since when I added the third section by clicking insert after section 2, by default it put 0 there. So we went up 5 degrees of dihedral for the first section, and then it's back to flat at 0 degrees for the second section. I could make it also 5 to match, and now we have a straight line dihedral. You could of course have a polyhedral and do something like 15. Just mess around with it. I think it's pretty intuitive. Let's move on. Twist is again similar to dihedral in that you're specifying an angle, but the thing is you're specifying the rotation of a section. It's not a, and so since it's a property of each section, that means you do actually have 3 angles there. Let me get rid of this third panel since it was superfluous anyway. So you can put 10 degrees twist on the root panel, and so that's kind of at some incidence angle as we talked about, but then the tip airfoil is still straight because it's at 0. I could make it match 10 degrees also, but that's kind of pointless because you can just tilt the whole thing in the wing properties. So I'll show you. If you click save and close, tilt angle, this will do it too. So that just tilted it about the nose 10 degrees. So there's dihedral, twist, foil, and then there's these panel details. So the panels are how the XFLR breaks down the CFD problem, computational fluid dynamics, how it breaks it down into discrete elements in order to figure out the lift and drag and all that. I think the default X panels is not enough. I'd recommend increasing it to 17 for most problems. This one, and since it's a delta wing, the chord is so large at the root, I'm actually going to increase it even further to 33. Another thing, for some reason, I've found odd numbers work better. Yeah, that's all I have to say about that. Now, the Y panels similarly is how dense the panels are in the Y direction. So if I make this 50, you can see that there's a ton of panels, ton more panels in the Y direction now. Oh yeah, so left click to drag this guy around, middle click to rotate it. If you're on Mac, I have no idea. This is all PC. Sorry. Now the distribution of the panels, by default it'll give you cosine for the X distribution, and this is, if you think about a cosine function, you start off at 1 and then you dip down and you come back up after 2 pi. And so it's really dense near the leading edge. All the panels are really close to each other, and then it dips down. Things get rare. The relative density, I mean, of the panels. The density is lower, and then the density increases again once you get to the trailing edge. So if you had a uniform distribution, which is the only other option, you can see that they're evenly spaced. But the cosine, I think, is that's default for a reason. It's a good idea because you want more panels if things are changing more, and you expect the flow field to be changing a lot, particularly near the leading edge, but also near the trailing edge. And so you want to capture all those effects. Similarly, in the y-axis, things are changing a lot near the wingtip, and so you want more panels at the wingtip. And the default here is minus sine, which also is exactly what we want, putting tons of panels at the wingtip. That's what uniform looks like. I don't know why they give you these other options, but they're there for you. Honestly, I've only ever used uniform and minus sine when it comes to the Y distribution. Again, I think if you just play around with these, you'll get the hang of it real quick. So that's the basic interface, which everything pretty much in XFLR uses. Now we can go back to the vehicle. So let's close out of this. Save and close. Down here. And that was for the main wing. We just defined it. You can also change where it is mounted to the vehicle. So let's turn off the fin and elevator for a moment, because those are kind of getting in the way. I'm hitting the shortcut to bring up the plane editor and verifying VIG and medium that I'm changing the right thing. But the shortcut is Control P or Shift F3. But again, you just plane, current plane, edit. So you can, for instance, mount the main wing 300 meters back from the origin. So now there's a scap of 300 meters. Or you can offset it vertically, like 300 meters above the origin. Now, you'll note here that XFLR is using a different convention than what we normally use in aerospace. It's using, by default, positive X going from the nose back to the tail, where normally in aerospace, positive X goes from the tail forward through the nose. And Y is still out the right wing, which means in this convention, Z is vertical up through the plane by the right-hand rule, whereas normally it's down through the bottom of the plane. Looks like these controls just manipulate how you view it. Unfortunately, there's no way to change its convention, so you'll just have to deal with it. But again, it's pretty easy to get a hang of. So I'm going to reset oops, those offsets. Okay. Except for the X one, I actually do want some X offset there. But again, I'll consult my sheet of paper exactly how much that is. I'll ballpark it as 500. So you continue this process specifying the other things on the vehicle. It says elevator here. This is not actually to specify control surface. This is to specify the stabilizer, the horizontal stabilizer. You do control surfaces differently, so I think it's kind of a misnomer, so just be wary of that. And fin is for vertical stabilizer. So I'll do the fin real quick as an example because it's a little bit different than the handling of the other wings. So you'll notice that this one, like the others, you have an X offset option, a Z offset, but you also have Y. And that's only available to you if you click double fin. And so if you have two fins, they're separated from the center by some distance, which you're specifying there with Y. So I actually want winglets on this vehicle, so I am going to specify 600 millimeters for that. Since I know my half span is 600 millimeters, that means it will place, sorry for hitting the mic, it'll place the winglets right at the outer panel, the outer section that I defined previously. The leading edge is 500 millimeters from the origin, and the outer panel has an offset of 1150. So I need this to be back 1650. And then I can go about my business actually defining it. And again, that's normal. I'll just throw in the default there. Oh, how come no one told me I screwed it up? I wanted 1650 for the X. And the Y again is half the span, so 600. Much better. So you can see the leading edge of the fin that I just defined is at the same location as the leading edge of the outer section of the main wing. Okay, so I'm going to go through and do all my geometry, check the boxes for another wing, a canard up front. I could check the box for elevator instead. It really doesn't matter which one you do. It treats all three of these as the same, honestly. And then I'll catch up with you soon. Okay.